I'm going to be finishing up the dividend or the investment design case. I'm just spending a couple minutes on it, and then we're going to get into the second half of the design equation, which is normalization. So today we'll go over the terminology and concepts with normalization. Next Tuesday we will go over a case study associated with normalization. Same idea, which is that having a hands-on case study seems to really improve the homework assignments and the exam. Also, I'm holding office hours today right after class to 3 because I have to leave campus at 3 o'clock. So sorry, I can't do them from 3:30 to 4:30 as I normally would. So today it's from right after class until 3 o'clock. Okay. So what I wanted to finish up with from last time was the end of class. I said that this holding item, where it's each investor's holding of a stock contains information about the stock's ticker symbol, the stock's name, and the number of shares that the number of shares that they've accumulated. What it really is a holding represents a relationship. I have it here, own. Another word suggested from the title was holding, so you might also say, holds stocks. So an investor holds 0 or more stocks, and a stock may be held by 1 or more investors. We assume that if the stock is not held by any investor, then we would not hold it in our database. It's just like a product we don't carry. If we don't have anyone invested in the stock, there's no reason to have it in our database. Therefore, the participation rate for the stock is 1. Whereas an investor, we don't require them to hold any stock. Maybe they're a market timer and they've sold out of their stocks. Maybe they're a new client and haven't had a chance yet to invest in any stocks, but 0 to many. So the thing I'd left you with last time is if the description of an item is pretty complicated, like it was in D and J, and mentions multiple entities, you should strongly suspect either an end-to-end or a multi-way relationship is involved. It's a strong tip-off that that's what's going on. Also in my solution, I showed dividend-paying stocks as a separate entity. That's unnecessary, but I was just showing it as an example. So in I, it said that the dividend per share is determined by the stock. So some stocks pay dividends and some don't. So even though it's not a multi-valued attribute, you could decide that if there's going to be a lot of nulls in that column, you might decide to split it out as a separate entity like that. So I just did it there. That's actually what the book calls a weak entity. So I did want to give you an example of what the book calls a weak entity. It's not exactly a multi-valued attribute, but the fact that it's 0 or 1 in some sense makes it that way. So a stock pays either no dividend or 1 dividend, and then the dividend for a stock is, if the stock pays it, it's for that particular stock. Okay? So it's not a bad idea to explicitly represent this relationship in the ER diagram. It's not something that I would deduct points for if you didn't do it. But anytime you have anything that resembles an optional attribute, it's not a bad idea in the ER diagram to split it out as a weak entity. Okay, so that's what I did here. This is an optional, just a second. Okay, so anything that's optional, you might consider any attribute, any optional attribute, you may want to represent as a weak entity. And then obviously in the database itself, probably you would just make this be a column that's associated with the stock, but by putting it out this way, it kind of makes it clear that it's an optional attribute rather than being a required one. Normally, when you show attributes, they tend to be required attributes in your ER diagrams. So is there any questions about this? Okay, so you'll be doing something like that in the homework assignment as well. You also may have noticed, well, most of you have not started the homework 4, but you may actually realize when you get to homework 4 that part of that homework I put into the quiz from last time. So you'll have a nice little head start on the homework assignment. Okay, so today, topic of the day, normalization. And actually, I wish I'd sent out an announcement about it. You may want to look at my slides online as I go through this, because it can be handy to have a copy of the staff branch relation in front of you, which is on slide 6. So normalization is a technique where we decompose a relation into smaller relations based on groupings of logically related attributes and based on the functional dependencies among those attributes. And as I said before, it's a bottom-up design technique. And typically, in the most general sense, you go from what is called the universal relation. So the universal relation is a single relation that contains all attributes in the database that you are modeling. So you jam all the information together into a single relation. So it's a single relation that contains all attributes you wish to store. And then the idea with normalization is that you decompose this universal relation into the final set of relations that you want. Now in practice, that's typically not the way we don't start from the universal relation. We typically start from forms, and we take the information from a form, put it into a relation, and if necessary, decompose it. But in the most abstract sense, we start with a single relation that models all attributes in our organization, and then we decompose that particular relation. And the goal of normalization is to reduce the possibility of having inconsistent data and to also reduce redundant data in the database. And those two goals are interrelated, because the less redundant information you have, the less likely it is that you're going to have an inconsistency, because the inconsistency comes about when you have redundant data and two things disagree. So for example, you have a property belonging to branch B007 and being managed by a staff member at branch B003, that's inconsistent. It's either at B007 or it's at B003, but it's not both. Okay? And you can use it in one of two ways. You can either use it as a bottom-up design technique, or you can use it the way I use it, which is as a check on my relations that I get from doing an ER diagram. So personally, I prefer to model data from a top level using ER diagrams. I get my relations from the ER diagrams, and then I use normalization to verify that the relations don't have any inconsistencies or redundancies. And just based on what we've already talked about, what typically, if we can manage it, what is the only redundant information we hold in our database? There's one kind of information that's redundant that we can't eliminate. Foreign keys. So at its heart, normalization is about decomposing relations about foreign keys. Essentially, finding foreign keys, breaking apart relations around foreign keys. But before we get to that, basically want to look at what happens, the three kinds of anomalies you can get if you have redundant information. So this is that staff branch relation I was talking about. Thus far, you've seen it as two separate relations, a staff relation and a branch relation. But let's pretend for a moment that the way we designed it was as a single relation, so that we kept with every staff member the staff member's number, their name, their position, their salary, their branch number, and the branch address. And we don't have a separate branch relation because all the information associated with a branch is contained in the staff branch relation. So this seems nice. We only need one relation, right? And we've got instantly at our fingertips what the branch address is. It's like having a phone book. Okay, this is a little bit like a phone book or a roster. Okay, but the problem is it has redundant data. So the branch address is redundant. And if I change the branch address of B003, I have to update it in all three locations in this particular relation. And if I forget to update it in even one place, then I'll have inconsistent data. Okay, so that's an example of what we call an update anomaly. There's also what we call insertion anomalies. So we may want to insert a branch that has no staff. Maybe we just are building a new branch because we've been so successful, and it's going to be branch V10 at 12 Cardiff Road. And it doesn't yet have any staff because it's under construction, but we want to put it in our relation. Well, the problem is that in order to do it, there has to be some values associated with these fields. Okay, now I might say I'll put nulls in here. But what's the problem with using nulls for those four columns? Oh, yeah, you got it. Because the staff number is a primary key, and you're not allowed to use null for a primary key. So you'd be violating what's called entity integrity. Remember, entity integrity requires that the primary key be non-null. So you get what's called an insertion anomaly because you either have to invent a fictitious staff member in order to insert a branch into this relation, or you simply can't do it until you've actually assigned a real staff member to it. So that's called an insertion anomaly. okay? And as I say, either the insert fails or you have to invent a fictitious staff member. And that's not really a great thing to have fictitious data in your database. Okay, we already went over an update anomaly. There's also what's called a delete anomaly. So let's say that I were to delete all the staff. Well, let's say I delete Mary Howe from the database. Okay, what happens to the information for branch B007? It's gone. So this is called a deletion anomaly because in the process of deleting a staff member, we inadvertently deleted information about the branch as well. And this is an extreme example. You normally wouldn't ever get to a situation where you deleted all staff associated with a branch, but you could certainly run into that problem with other relations that you form. So it just shows you that this particular relation is actually subject to multiple types of anomalies. So insertion is where you can't insert into a relation because you need to leave some columns null. And if you were to do that, it would fail because the primary key would be null. That's an insertion anomaly. The update anomaly is that you change a piece of redundant data, and if you don't change it everywhere, you'll have inconsistency. And the delete anomaly is that if you delete a tuple from the relation, you may inadvertently lose information about an entity. Okay, the basic problem here is what? Just kind of at an intuitive level, what's the basic problem? Yes, very good. Exactly right. We combined entities. So we're putting both the staff and the branch in the same relation. So intuitively, each entity should have its own relation. Okay, and that's what the ER diagram naturally does for us. The ER diagram naturally puts each entity as an independent square, and you automatically create a separate relation for it. So with ER diagrams, you'd be really unlikely to come up with this particular situation. Okay, but in general, if you combine two entities in the same relation, that's where you're going to run into difficulties. Okay? So when you are doing normalization, what you want to do, remember we're decomposing or splitting a relation into two or more parts. So when we break it, so what we're doing is we're taking a relation and we're breaking it into two or more parts. In this case, we're breaking it into 3 parts. So when we decompose it like that, we need to ensure that 2 properties are met. First of all, the lossless join property says that we can join these 3 relations, I'll call them R1, R2, and R3, back to get the original relation. So it must be the case that you can join R1 with R2 with R3, and you will get the original relation back. That's the lossless join property. And then you also need to ensure that any constraint, any integrity constraint enforced in the original relation is still enforced in one of the 3 subrelations. So that every constraint migrates down to one of the decomposed relations. Those are the 2 properties you seek to maintain. And normalization, the way you maintain dependencies and the way you also maintain the lossless join is it's all based on something called functional dependencies. Okay, and a functional dependency describes relationships among attributes. ER diagrams define relationships among entities. Functional dependencies define relationships between attributes. And we say that B is functionally dependent on A if each unique value of A is associated with exactly one value of B. Okay, so it's kind of like a key. Remember, a key uniquely defines a tuple. It's not quite like that, but each unique value of A has exactly one value in B. Okay, so staff number uniquely determines a staff member's name. Okay, and it also uniquely determines that person's position. But a position does not uniquely determine a staff number. For example, we might have sales associate, and presumably we have multiple sales associates in our firm, so that's not going to be unique. Even this one, staff name determines staff number, may not hold. Okay, you could have some very common names like John Smith, and if you're a large company like Amazon, you may have 2 John Smiths in your organization. So the requirement is that the A, each value of A uniquely determines a value in B. And you just see what I had said a moment ago. Position is not able to functionally determine a staff number, but a staff number functionally determines a position. Okay, and we call, how many people are taking 370 this semester? Well, you're going to have 2 different definitions of a determinant. Okay, so there's the definition of a determinant associated with a matrix. Guess if you had Math 251, you probably also learned the determinant of a matrix, right? Well, this is different. So the determinant of a functional dependency is the attributes on the left-hand side of the arrow. So we write a functional dependency using an arrow, much like you did in CS 311. So if we have, say, A, D, E determines F, X, Y, we would call A, D, and E the determinant. So a functional dependency can have more than one attribute. It's not just like the functions in programming languages can have multiple arguments. Okay, and when you define a functional dependency, it's something that needs to exist for all time across all data. It's very easy to look at sample data and get deceived. So if you go back and look at the staff-branch relation, it would be very easy to come to the conclusion that staff name uniquely determines staff number, because just looking at that, there's no duplicated staff name. In fact, no, salary doesn't. Every other piece of data is duplicated there, but staff name isn't. So you have to be very careful not to be taken in by sample data. You have to make sure that when you define a functional dependency that it really holds, not just for the sample data that you're looking at. Okay, so that's all that those slides said. Now, when we talk about functional dependencies, we want the determinant to be the minimum possible number of attributes. Just like, remember, we had super keys versus candidate keys. Okay, same thing here. When we have a determinant that's a minimum determinant, we say that that defines a full functional dependency. And if we have too many attributes, not a minimal set, might be nice if we were consistent with our terminology and called it a super functional dependency, but we don't. We call it a partial dependency. Okay? So it's true that a staff number and a staff name uniquely determine a branch number, but it's also true that by itself a staff number determines a branch number. Therefore, we call this dependency a full functional dependency, and we call the first one a partial functional dependency. I find that to be confusing. Does anyone know why I find it confusing? And I always have to fight it in my mind. Yeah, usually full means more than partial. Here, partial means more than full. So I find that this is not, I often find myself fuzzy on this, and but it's just the way it is. Partial dependencies actually have a superset of attributes, and full dependencies, or functional dependencies, have proper subsets. Okay, so you just got to get used to that fact. Okay, so that's just summing it up. And this should be something you remember from CS 311, right? Functional dependencies are one-to-one mapping from the left side to the right side. Holds for all time, and the determinant has the minimum number of necessary attributes. Okay. Then there's also something called a transitive dependency. And you should all be familiar with those. So if A determines B and B determines C, then A determines C. Okay, so an example might be that a property number determines an owner's number, and an owner number determines the owner's name. So that means the transitive dependency is property number determines owner name. We try not to explicitly represent transitive dependencies. Transitive dependencies are implied dependencies. So we do not explicitly represent transitive dependencies. Okay, they are implied. So this one, we would write out these two, whereas this one, I know I'm doing it in green, that one we would not write out because it's a transitive dependency. So if you're creating, if on the homework assignment or on a test, I ask you for the full functional dependencies for a relation, I don't want you to write down a transitive dependency. Yes, it is a full functional dependency, but it's redundant. So a transitive dependency is a redundant dependency. Again, it's not a minimal one. It can be derived from two other dependencies. Okay, there's another one, pretty easy. I'll let you just look at the slides. I know I'm going fast. The reason I'm going fast is A, it's not rocket science. B, it should be a review of CS311, and C, it's not the most scintillating material you've ever seen in your lives, okay? So you can easily read about it later if I'm going a little fast for you. Okay, so let's say that we want to identify a set of functional dependencies for the staff-branch relation. A lot of it's using your common sense, or let's go back. This is actually one where we can have participation. So using some common sense, what are some functional dependencies here? Other than staff number uniquely determines everything. We'll get here. I'll do the easy one. Staff number determines staff name, position, salary, branch number, and branch address. So you don't get to do that one. Okay. What are some other ones here? Yes, Tyler.
Branch number identifies the branch address.
Yes, branch number determines the branch address. Okay, what might be another one? Some of these may not be as obvious now. So I think that is a reasonable one, that the position may well determine the salary. Okay, that was one I didn't think is super obvious, but I think that's a reasonable. Now, actually, that's not true there. Okay? So, but I would think oftentimes, like at UT, there's position codes and they at least define a range of salaries. Now, I believe the book made the claim that a branch number and a position determined a salary. So that would be something you would get presumably by interviewing people. So that's a good one. There's one more in here. Yes, Tyler?
Doesn't the branch number identify the salary?
No, because you could have a manager and a sales associate. I'm sure the sales associate would love to make the manager's salary, but just like I'd love to make the president's salary. No, actually, I'd like Butch Jones's salary. So, no such luck. This one's like a magician's trick. There's a bit of illusion here. So, there's probably you could argue you could have two identical street addresses with cities, but I don't really think that's particularly reasonable. I think you'd be hard pressed to find, because that address contained a street number, a road, and a city. I think you would be hard pressed to come up with two different branches at the same street address and same city. So I think it's reasonable to reverse it. So this one and this one are in effect one-to-one. What is it, a bijection, I think? I forget. It's been a long time since I took discrete math. At any rate, those are the four that I believe the book came up with. Not mistaken. Yep. So they branch, and then, so once you came up with this, that must also be the case. So if the branch number and the position uniquely identify the salary, then the branch address and the position must also uniquely identify the salary. So any questions about that? Usually I wouldn't in a homework assignment or a test, I'm not just going to give you a table and say have at it. Okay, I'm going to give you a set of steps, just like you saw in the investment design study, and from that description you should be able to derive functional dependencies. Now they could be buried, just like the relationships, attributes, and entities were buried in the investment design thing, and you have to kind of tease them out. Okay, so functional dependencies then give you an opportunity to identify integrity constraints. The big one is entity integrity, the primary key. Okay, but also referential integrity. They kind of allow you to start to identify foreign keys. So functional dependencies tend to allow you to get your primary keys and start to think about your foreign keys. Okay, this is so repetitive. Identify your candidate keys, then you choose one of them to be your primary key, and you want your, let's see, this is all obvious. Okay, so you pick your primary key from your candidate key, and then normalization is either a decomposition on a primary key or it's a decomposition on the candidate keys. Well, we're going to, in this course, just to simplify things, do decompositions on primary keys. But at the very end of the lecture, or if I don't get to it, then next time I'll show you a decomposition using candidate keys. Okay, and the normal forms, there's a whole set of them, so researchers went crazy, got all kinds of papers out of them, and believe that usually you go up through what's called BCNF, which is Boyce-Codd normal form, although in this course we're only going to go up through third normal form. The higher you get, the more restricted you are and the less subject you are to update anomalies, but it turns out that at some point you start to reintroduce other problems. Just like with chasm traps, they solved one problem but introduced redundant information. Once you get up, I think, beyond Boyce-Codd normal form, I think once you get up to fourth normal form, while it's stronger, you're also, I believe, starting to give up efficiency or you're introducing other problems. So higher normal forms are definitely good up through, I believe, Boyce-Codd normal form. Beyond that, you may be into trade-offs between data consistency and efficiency. Okay, so you start with unnormalized form, and the book unhelpfully talks about repeating groups. I thought I had removed this. Multi-valued attributes is what they mean when they talk about repeating groups. So you start, if you're going to do the bottom up, so if you're doing it bottom up and you're not using ER diagrams, you basically are taking forms and you're converting them into relations. Taking the obvious thing, you take the information off of the forms, and each thing like name, salary, address, social security number, each of them becomes a column. And the rows are whatever data is contained on a single one of those forms. So to get to first normal form, you eliminate multi-valued attributes. So this is a nice way of saying that you go from unnormalized normal form to first normal form by eliminating multi-valued attributes. Okay, and I've showed you two solutions to the problem of multi-valued attributes. Okay, what are they? Give me one. Replicated columns, the evil one. And what is the one I prefer? Second relation. Split the multi-valued attribute into a second relation with the primary key. Okay, so the evil solution is number one here. And the, I'll say, I won't say evil, I'll say disgusting. A little bit different versus elegant. Okay, the only problem with the elegant solution, you might argue it could be less efficient. Clearly, if you don't have, because the way that you recreate the multi-valued attribute is with a join, whereas with the disgusting solution, the data is all in one table. It's just that it makes the process of writing the query so painful that I think you give up the efficiency for ease of use. Okay, we come back to that in a couple of weeks with scripting languages which do the same thing. They trade off ease of use with efficiency. So especially for those of you who are graduate students, when you get to the project in a few weeks, you'll be dealing with multi-valued attributes in your project. I definitely want you splitting them off into a separate relation. So that's how you go from unnormalized normal form to first normal form. Okay, you simply split off your multi-valued attributes. Then, to get to second normal form, you need to remove all partial dependencies. So if you have a partial dependency on the primary key, you need to decompose them. Okay, the easiest way to show you is through an example, and then we'll come back to it. Okay, so let's say that this is a lease. Okay, this looks like a lease form, right? It's got client number, property number, client name, property address, when the start date is, when the finish date is, what the rent is, what the owner number is, and what the owner name is. You might see all of this on a lease form. So if we just copy all the attributes of a lease form into a table, this is what we get. And now what we want to do is find the functional dependencies. And what we want, and I have it illustrated here, is the full functional dependencies. We don't want partial functional dependencies here. So if you start to look at it, you would see that the client number and the property number uniquely determine everything. Okay, they actually uniquely determine the client name, the property address, the rent start, the rent finish, the rent, the owner number, and the owner name. Okay? Now, you might say, then why don't we have arrows here, 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 and here? Okay, instead, the only arrows are this one, this one, this one. Oops. There we go. Rent, whoa, is that right? Yes, rent start and rent finish. Okay, the reason we only have those two is because client number determines the client name, so this one right here, and the property number determines these other ones. So what we would be saying is if we included all the other attributes like client name, property address, rent owner number, and owner name in this first relation, we have then a partial dependency because we can, with a smaller set of attributes, uniquely determine the client name by just using the client number, and we can uniquely determine the property address, the rent, the owner number, and the owner name just using the property number. So if we have a full functional dependency, we're only representing the set of attributes that is necessary, that requires that complete set to uniquely identify them. Okay? We don't need both client number and property number to uniquely determine a client name. We only need the client number for that. Therefore, that first dependency right here does not include client name. For the same reason, it doesn't include property address because a subset of those attributes, namely property number, is able to determine property address. Okay, so the first three are giving us client number and property number, determine rent start and rent finish. Now, let me get more room. So we have client number, property number, determine rent start and rent finish. Then we have client number by itself uniquely determines client name. We have property number by itself uniquely determines property address, rent, and owner number. Okay, and I could put here owner name, but what's the problem with putting owner name in there? Yep, owner number actually determines owner name, and I said that we don't explicitly represent transitive dependencies. So we don't include owner name in there because that would be explicitly representing a transitive dependency. Okay, and actually I shouldn't have done it here. This should not have been, that's unfortunate. This really should not have been here. Actually, that's not true. It was fine for it to be there. It's just that when you actually write down the functional dependencies, then this should not be here because it is a transitive dependency. So it was fine to put it here, but when I actually write down the functional dependency, it shouldn't be there. Okay, so client number and property number are a primary key, but there's actually two other candidate keys in here. Okay, so if you look at it, it's also the case that client number and rent start, if we make the assumption that a client can't be in two houses at once, which is kind of reasonable, then we can say that the client number and the starting rent determines the property number and the, let's see, that it really doesn't, let's see, determines property number, rent finish, and also, let's see, property number. This would be a little more dubious. No, that's not. Property number and rent start, if we only rent to one client at a time, determines client number and rent finish. Okay. They also determine all those other things. The reason all the other, wait a minute, just a second, I'm going, this is bad. No, I do have, okay, I have to include all the attributes in here. So determines property number, rent finish, property address, rent, owner number. Technically, I have to. Okay. But then, once I have that, I say, okay, this is a transitive dependency because what? Why am I including a transitive dependency in there? There's a transitive dependency in here. Yep. So when I really write it down as a functional dependency, I should only include this part because I can get property number determining the rest of it. Okay, there's another, based on what you see here, so this is functional dependency 1. This was client number, functional dependency 2, 3, 4, 5, 6. There's 2 more. Yes. You got it. So you also can have client number and rent finish because presumably that's also going to be unique. It's going to determine a property number and a rent start. And same thing, a property number and a rent finish should determine a client number and a rent start. Okay, so we have these 8 functional dependencies. Now, the primary key, we just have to choose it. We're going to choose the primary key to be the client number and the property number. So there's actually 5 candidate keys. 5 through 8 define also candidate keys. But we're going to choose client number and property number as our primary key. So to get from first normal form to second normal form, what we need to do is decompose this relation based on partial dependencies on the primary key. Okay, so there are 2 partial dependencies here because the primary key consists of 2 attributes. So the first partial dependency is 3, and the second partial dependency was not 4. First partial dependency is 2. So the first partial dependency is 2, second partial dependency is 3. Okay, so our primary, so basically we're finding any dependencies whose determinant is a subset of the primary key. And we're going to take that set of attributes and put it off in its own relation. And that determinant will be the foreign key in that relation. So what we're going to do is here, we're going to create one relation from that set of attributes, a second relation from this set of attributes, and what will be left is this particular relation. Okay, so we end up, this is functional dependency 1, partial dependency 1. This is the second partial dependency. And when we've removed everything on the right-hand side from the original relation, this is what we're left with. Whoops. Okay, so what we're doing is we find, let's go back. So to go from first normal form to second normal form, identify the primary key, identify the functional dependencies. So if partial dependencies exist on the primary key, so a partial dependency, so if there is a dependency, functional dependency, whose determinant is a proper subset of the primary key, then this dependency is a partial dependency. Okay, so what we do is we remove all the right-hand attributes from the original relation and move them to a new relation, and we copy the left-hand side into the new relation. Okay, so that's what we're saying here. It says if partial dependencies exist on the primary key, remove them by placing them in a new relation. What it really means is by placing the right-hand side attributes in a new relation along with a copy of their determinant. So the determinant, it becomes the foreign key. Okay, so the copy of the determinant is the foreign key in the new relation. It's what allows us to join this new relation to get back the old relation. I want to say in the new relation. So we remove, for each partial dependency, we remove that set from the original relation, move the right-hand side attributes over, copy the determinant attributes over. Okay? One nice thing, you might say, well, let's say that the primary key consists of A and B. Okay? And let's say A determines some set of attributes X, and let's say B determines some set of attributes Y. And one question you might ask is, can X intersect Y be anything other than the empty set? And as far as I know, the intersection of x and y will be the empty set. So there won't be any overlap between the two. If A uniquely determines the values of x, B is not going to be uniquely determining the values of x. It's going to be one or the other. So the attributes that you end up moving, you'll have one relation that's AX and one relation that's BY, and there's not going to be any overlap in those attributes. Okay, and then you'll have your remaining relation, which is whatever, if AB went to, say, Z, you'll still have AB in what is Z minus X minus Y. So whatever is left over after you've subtracted X and Y. So that gets you your second normal form. And there's an important thing that I don't want you to miss right here. If the primary key is a single attribute, then the relation is in second normal form if it's in first normal form. Why do I know that? Why do I know that any relation that has a single attribute primary key? Looks like you're scratching, okay. Yes?
Do you not have any partial dependencies?
Exactly. You can't have any partial dependencies because in order to have a partial dependency, the determinant has to be a proper subset of the primary key. Can you have a proper subset of one attribute? No. Right? You can't have a proper subset of one attribute. Therefore, if the primary key is a single attribute, the relation is already in second normal form. So guess what? On your homework and on the test, you're never getting a relation where the primary key is going to be a single attribute, because that would make it completely boring. Okay? So here's the other thing. Actually, I wasn't quite all the way truthful with you there. So not only do we move the right-hand side attributes, but we also move any attributes that are transitively determined by the right-hand side attributes. Okay, so this one, so owner name is a transitively determined attribute. Okay, it was determined by owner number. So when we move the right-hand side attributes, to a new relation, we must also move any transitively determined attributes. So that's an important caveat. You have to make sure that you transfer over any attributes that are transitively determined by the right-hand side attributes. So owner name moved out as well in this case. Okay, and the important thing here is I can reconstitute the original relation via joins on the determinant attributes. So the determinant attributes were property number and client number. If I do a join of those two with the rental relation, then I reconstitute the original lease relation. Questions about that? Okay, this is the hard one. The next one's a lot easier. Okay, to go from second normal form to third normal form, you're simply finding your transitive dependencies and moving the right-hand side attributes determined by your transitive dependencies to new relations. So in this case, we have this functional dependency of owner number determines owner name. If we come back here, that was this was the one that I had numbered 4. So that's a transitive dependency. So we get to third normal form by removing transitive dependencies. So in this case, we're going to move owner name to its own relation, and then we also move a copy of the determinant. Okay, so again, identify the transitive dependencies, move the, by placing the right-hand side attributes in a new relation along with a copy of their determinant. Okay, it's possible that this is recursive. Okay, so we have owner number determines owner name. Let's say owner name, I don't know. I know owner name can't really determine anything, but theoretically, you could have something like this. You could have A determines, you could have a relation like this. X, A, B, C, and you could have A determines B, and you have B determines C. So your first step would be to take and form a new relation with A, B, okay, because this is the dependency, and you'd have to bring along C because it depended on B. But then you'd have to recursively decompose that because B depended on C, so you'd end up with the relations XA, AB, BC. But that would be hugely unlikely. I've actually never seen that recursive kind of decomposition. Typically, there's only a one-level decomposition there. Does that make sense? You could theoretically have multiple transitive dependencies on the right-hand side. Okay, but it'd be really rare. So in this case, we have we decomposed the property for rent by moving the owner name into its own relation. We moved a copy of the determinant, so that's a copy of the determinant. We preserved the lossless join because if we join the two owner numbers, we get the original relation back. Okay? So that's third normal form. Okay, so this was all based on primary keys. Now, this is enough that I'll do this one. You're probably overwhelmed enough that I will do the last part of it on Tuesday. So Tuesday, we'll do a quick review of this because I know this is one of the most difficult lectures of the semester, so I'll do a quick review. talk about generalized normal form, and then we'll walk through a case study. I think the case study will make things a lot more understandable. Like I asked you to do with the investment design study, please take a couple minutes before class to read through that case study on Tuesday, so you're kind of ready to go with it when we start. And I'll see you Thursday or next Tuesday.